Hello everyone. This video is to go over how to calculate out the range of an object when only the initial velocity and the angle that it's launched at is given. There is a caveat to this particular derivation, and that is I am assuming that the starting height and the ending height are going to be the same. So think of a football field and or a soccer field or a field hockey field where the playing field is level. So I'm interested in figuring out what the range is, which is the horizontal motion. So I need to find out how much of the velocity vector, the initial velocity vector, is going in the x direction and how much of it is going in the y direction. So as you can kind of see in the diagram, I'm trying to find the components of this vector. Vx is the velocity in the x direction, the horizontal motion, and Vy is the initial vertical velocity of the object. And just to be sure you understand what I'm trying to solve for, the horizontal range, again, if the object starts at this location and lands in this location, this horizontal distance that it moves is considered the range. So to figure out the horizontal range, or the x value, we simply take the velocity in the x direction and we're going to multiply it by the time in the air, just like if it was moving at a constant velocity, because it is. We know that the velocity in the x direction is just the initial velocity multiplied by the cosine of the angle given in the previous diagram. And to start off with, I'm going to take equation number 2 and substitute it into equation number 1. So the horizontal range is just going to be the initial velocity we throw it at multiplied by the cosine of theta multiplied by the time that it's in the air for. How long the object is going to be in the air for is simply a function of how quickly it's moving upward to start with. Hopefully that particular idea makes sense. The faster the object is moving upward, the longer it's going to be in the air for, and the greater range that we potentially could have here. So what I am going to do is try and break down this motion into 2 bits and pieces. And I'm only focusing on the vertical component of the motion to begin with. At its release, or being fired, or whatever happens to be happening in the problem, the initial velocity in the vertical direction is going to be its largest value, that Vi is going to be big, and the object is going to slow down in the vertical direction over time until it finally reaches its peak. At that particular point in time, the object will reverse directions. The time to get to the peak is a relatively simple calculation to work out. We simply just have to take the equation for the acceleration of an object, and we can quickly derive equation number 4 that I have here, that the time is just the change in the velocity divided by g. So the initial velocity in the upward direction ends up being the number that's in the numerator, because the final velocity at the peak in the vertical direction is 0, and that just gets divided by the acceleration due to gravity. This is the time to the peak. And again, because I know that it's going to be on a level playing field, the time to the peak and the time back to the bottom to the same level again is going to be the same. So we need to double that time to the peak in order to get the total time. So the final velocity to the final velocity of the peak would be 0, and the initial velocity would be v sine theta. Substituting that in and solving that for the time, we get 2 times vi sine theta over g, which is just the which is equation number 5 that we have here. Finally, we're going to substitute equation 5 into equation number 3. The range is going to be v, the initial velocity, times the cosine of theta, multiplied by 2 v sine theta all over g, and then kind of getting it into a format that was a little bit more user-friendly. V times v is going to be v squared. I still have a 2 cosine theta, and then all over g. Some of the math geeks in the class, or math nerds, be proud right at the moment. 2 cosine theta sine theta is a double angle formula in trigonometry, so we can reduce all of that just down to sine of 2 theta, what we have in equation number 7. And that's going to leave us with that the horizontal range for any projectile that is going to start and end at the same height is simply the initial velocity of that object squared, multiplied by sine of 2 theta divided by g. Interestingly enough, this means that any range that you would have, a possibility of ranges, will have 2 angles that end up working and give exactly the same range. So, for example, 30 and 90 will yield the same range. 20 and 70 will yield the same range. 10 and 80, as far as the angles are concerned, will yield the same range. Anyway, this equation here, equation number 8, it's kind of nice to have in the back pocket in case you need it. If the problem suits it, then you can use that to help you out. I hope that you found this helpful. Thank you for watching.